Please use proper safety measures when working with lasers. The NUBB23 is a blue laser diode array outputting 22 watts of optical power. It consists of 4 high-power laser diodes and an integrated collimation lens array. It was designed for projection and lighting applications and provides exceptional radiation power for its size. With about $3 per watt, it is also very cost-effective. Note that the diode array needs to be mounted to a properly sized heatsink to prevent it from being damaged. Here you can see a close-up of the device, powered by a few milliamperes. Such a low current is well below the lasing threshold, and the diodes only output a faint glow of beautiful blue light. The rated current is 3 amperes, at which 22 watts of 450 nanometers light is produced. The collimation lens is attached at 4 points with an elastic glue to hold it in place. In this setup, the laser diodes are driven by an adjustable power supply. Note that all 4 diodes are connected in series inside the chip. The voltage is raised until the lasing threshold at about 370 mA is reached. When reaching the lasing threshold, the brightness suddenly increases dramatically and coherent laser light is emitted. Below the threshold, the light is not coherent and comparable to that of an LED. Next, the laser is pointed onto a sheet of paper, which is viewed from the backside. The laser is then moved from 0 to 1 meter, allowing the beam shape to be observed for different distances. As you can see, the collimation is not particularly good for long distances, but works well for the intended applications. In the far field at 3 meter distance, the spot size is about 50 by 14 millimeters. In these shots, the camera was set to grayscale mode. In color mode, monochromatic lights are usually challenging for JPEG compression and exposure controls, and produce washed-out images. We will now attempt to remove the collimation lens from the device to reveal what's underneath. As seen previously, it is attached at 4 points with glue, and a thin and sharp razor blade is utilized to carefully cut into the gap between the lens and the cover glass of the chip. Before inspecting the diode assembly, let's quickly take a look at the lens array. The lens appears to be made from molded glass and features an anti-reflection coating designed to transmit 450 nanometers light as well as possible. During the manufacturing, it is precisely aligned to the 4 diodes and then fixed in place using glue. After removing the lens, the construction of the device gives an unobscured view of the 4 laser diodes. The long semiconductor diodes with their golden bond wires can be observed much better than in the usual laser diode packages. The bluish squares on the left side are very small dichroic mirrors, which are precisely placed in front of each diode and are angled at 45 degrees to direct the beam outward. Since the laser diodes are now easily observable, let's take a closer look at them when powered up. To prevent damage to the camera, the device is again operated below threshold at a few milliamps. It is rare to have such a clear view at an operating laser diode. In this section, the beam profile of the uncollimated laser diode array at varying drive currents below and above threshold is presented. Due to the large brightness range, the shutter speed is adjusted in the middle to avoid overexposure. Note the speckle pattern above the lasing threshold. To respect viewers' expectations when creating a video about a high-power laser diode array, it appears mandatory to incorporate a demonstration of burning something. To this end, we will burn a piece of paper with the uncollimated beam and a few centimeters of distance. Remember that it is possible to focus all this energy to a spot size of a few hundred microns, with several orders of magnitude higher energy density. I would like to conclude this video by sharing a few more photographs of the device and hope you found the information provided interesting.